Okay, today let's talk about op-amp, operational amplifiers. Op-amp. Yeah. Op-amp is a voltage amplifier. It takes in the differential input voltage and it gives you output voltage. And it is probably the single most widely used electronic device. So let's see. And this is a picture from your textbook. I actually want to modify one thing. I want to actually call this one V1. Okay, for this case, actually, it doesn't matter. Okay, it doesn't matter. Because why? Because this plus terminal is directly connected to the ground. So whether you measure the voltage at this level with respect to the plus terminal or the ground, they're the same. Okay. So for other derivations, this is actually useful. Okay. So this is the op-amp. The actual op-amp is the triangle. Okay, this triangle. Okay, when you buy an op-amp from a store, it looks like this with a little black thingy with some legs sticking out. Okay, so you put in the V input. Okay, this is your voltage input, and op-amp will produce an output voltage. Okay, and then your output voltage V out. Okay, divided by the V in will be minus approximately negative RF divided by RI. Okay, so this is the equation that you have to remember. So how is that possible? Okay, so for an op-amp, you buy this little part, and then the rest of it you wire them. Okay, you choose the RI, you choose the RF, you wire all this. You wire the input voltage, and then you're gonna measure the output voltage. So first equation is an op-amp equation that says your V out is your V1, which is the difference between these two terminals, V1 times G. Okay. In the previous slide, I had a negative sign. Okay, they're both correct. In this case, this is correct because in the picture, you can see that I reversed the polarity. Okay, the polarity is when you put in the negative and positive, you get a positive negative voltage. Okay, so G, okay, for a typical op-amp is a very, very, very large number. Okay, very large number. So how does it work? For an op-amp, the current that goes into the op-amp, I3 right here, is nearly equals to 0. Okay, it doesn't take any current in. And what that means is that I1, okay, I1 that's going into that node is equal to I2 plus I3, but with I3 being 0, I1 is equal to I2. Okay. So now I'm writing I'm going to write out the loop law. Okay. So let's call this one equation 1. This is equation 2, equation 3. Okay. So equation 2 comes from taking a loop. Okay. This outer loop like this. Okay. So starting from VI, okay, you gain VI and you lose, you'll end up with a V output. The tilde shouldn't be there, that's a typo also. And the third one is a loop starting from here, the negative terminal, the VI, and go around, and this is your second loop. Okay, so this is your loop number 2. And this is your loop number 1. So when you go around the loop number 2, you have VI minus RI, this is typo, RI times I1 equals V1 at that level. Okay? So now we have to do some algebra. What's your goal? Your goal is to express V out in terms of V in, or find that ratio. Okay? So V out can be found here, here, and then V initial can be found here and here. Okay? So what do you have to get rid of? You have to get rid of the current. You have to eliminate current, I. So I can just use I because I1 is equal to I2. So eliminate I, and you have to eliminate V1 from the three equations that you see. So let's see. So first step is let's get rid of current. Using equation 3, your current 1 is VI minus V1 divided by RI. with the expression for the current, what you do is you go to equation number 2, which is VI minus RI plus RF. I took out the current because there's only one current in the system. Okay, so I'm just going to call it I1 equals your V out. So is that clear what I'm trying to do? I'm trying to relate the V out to V in, VI. Okay, so current needs to disappear. So now I'm going to plug that in here. So I have something like VI minus RI plus RF divided by RI. VI minus V1 equals to V out. So which equation haven't we used yet? That's equation number 1 that relate the V out to V1. V1 needs to go. So from this equation, I'm going to call this equation number 4. Equation number 4, I'm going to get rid of, I'm going to solve for V1. Let me see, where's V1? I see V1 right there. Okay. So V1, let me just multiply everything by RI first. So I have a VI RI minus RI plus RF times VI minus V1 that I don't want. I don't want the V1, so I want to solve for V1. And then multiply everything out. You'll see, I think this will cancel with the first term. Okay, this will go away. And you have a minus RI V, hang on. You'll have minus plus RI plus RF times V1. And then you have a RF times VI equals to V0. So finally, almost finally, V1 is, oh, I think I forgot to multiply this by RI. So you have a RI V out plus RF times VI divided by RI plus RF is the voltage level at the negative terminal. Okay? So now my next step is to plug this into equation number 1. Equation number 1. Oof. Okay? So equation number 1 is, what was it? It was a V out equals your G times V1. Yeah, so you have a G times V1, which is RI V0 plus RF times VI divided by RI plus RF. That's equal to V out. And you're going to do a final, okay, my final simplification. Okay. So here, once we plug it in the V0, V1, now we can simplify one more time. Okay, this is a little bit painful. You have a RI plus RF. What did I do? I did multiply by the denominator. V out equals to G times RI V0 plus G times RF times VI. Now move these terms over to the left-hand side. You'll have RI plus RF minus G times RI times V out equals to G times RF VI. So V out is G times RF times VI. I'm going to just pull this one out. Divided by RI plus RF minus RI times G. As you take a limit, okay, as G increases, what happens? These two terms become insignificant compared to the RI times G, and it becomes, your VO becomes, now you have, you only have these two terms remaining, okay, this one and this one. So when you divide, you get negative RF divided by RI times VI. Okay. Finally, we proved that equation. So it's actually quite simple. Okay, simple to just memorize that. So let's continue from last video. In last video, we derived the relationship between the V out and V in. And it turned out it applies in the S domain too. If you take a Laplace transform of the whole circuit, this will be an S domain. This is going to be an S domain. This one, your impedance will be 1 over CS. Okay? And the impedance of resistance is just the R. So now you have V out in the S domain over V in the S domain is equal to minus. That was RF, right? So the R divided by 1 over CS. Okay? It works in the S domain. It doesn't have to be in the time domain. So that's equal to minus RCS. Okay? So what is this? It says your V out is negative RCS times V in. What does that mean to multiply by S? Okay? That means in the time domain, okay, if you take an inverse Laplace transform, you have a V out in the time domain is minus RC times the derivative, okay, derivative of the V input. Okay, so this is called a differentiator circuit. Okay, it differentiates the signal and multiplies by RC and gives you an inverted Polarity, and it gives you as an output voltage. Okay, so this is a differentiator circuit. So op amp, you don't have to have just resistors. If you just use resistors, it will amplify the voltage by a constant number. But if you use a capacitor, combination of capacitor, you will differentiate the signal. What if you want to have an integrator circuit? What if you want to integrate the signal? And you can think about that. Yeah. So I wanted to show you other circuits. This picture is from a course, online course called Introduction to Electronics. Okay, and it's in Coursera. You can find it in Coursera. And then this is by Dr. Bonnie Ferry. Yeah, so you can find the course, and it's not. I don't think it's going to be too difficult for you if you're interested in more of e-courses. So let's see. Yeah, so this is a non-inverting amplifier. Okay, you can see this is looking very different from what we had. What did we have? We had minus plus. We had a V in. Oopsie. Okay, we had a V in. Okay, and going in. Oops, I didn't mean to do that. Okay, with the resistor. What happened? What happened to my? Okay. Here we go. Minus plus RI, and then here you have RF. Your V out. Here we go. Okay, so that was our configuration. You can see clearly that you wire, this is different circuit. So if you wire it this way, okay, your V out is going to be some constant times your V in. Okay, it's non-inverting because you're missing a negative sign there. So another circuit, it's a different circuit. What does it do? It spits at the difference between two voltages, V1 minus V2. These are both source voltages, and output is RF divided by R1 times the difference of these voltages. And by the way, there's a typo. This should be F. Okay. So let's try to do some homework. Okay. So obtain the transfer function V out over Vi in the S domain. So this portion right there, okay, this is your C in, and then this will be your C fine F. Okay, F. So what is V out over V in? S. That's equal to minus CF. That's a function of S. Oh, actually, that's just R3, and divided by C in. Okay. So where CF is simply R3, and then CI is combination of these three elements. So these two are in parallel. So let's replace that with the impedance 1 over CS. Okay. This is This is R2 that's in series. How do I in series? Okay, in series, I'm just gonna write that out. Okay, plus 1 over CS that's parallel to R1. Okay, this is just my own notation so that I can write it underneath. So this is whenever you have two elements that are in parallel, you can do product over sum. Okay, or you can do 1 over this CS plus 1 over that one, 1 over R1, add them together and then invert it. So that's still CI. So this is equal to, let me see, R2 plus, you have common denominator, you have R1CS plus 1, you have to invert it still. So that's equal to R2 plus R1CS plus 1, R1. Here it is, okay? So let's see. I think I'd like to simplify before plugging to this equation, okay? So what is this? This is R1, R2, CS plus R1 plus R2 divided by R1 CS plus 1. Did you follow that? I just use a common denominator and I'm going to plug it up there if I can remember all those terms. So let me see what's CF. That's R3 and then now you divide by, okay? Divide by CI. So you have a R1, R2, CS plus R1 plus R2 and then you have R1C S plus 1. Here it is. So let me get rid of that line. Okay, so this is your ratio transfer function, okay, of the V out over VI. Okay. And this is the, I think this was the homework problem. Okay, so now next we're going to go into the next lecture, which is going to be the last topic of chapter 6, and it's going to be about DC motor.